These are my collaborators. They have been more over the years, but these are really currently the people who I work with most closely. Alex Stokovsky, who is developing great methods to post-processing analysis of atomistic simulations. Alfredo Mettere, who is right here. Thomas Appelstrup, Nicola Bertland, and Tim Shu, all at Lawrence Livermore, and my former grad student, Rodrigo Freitas, who is now at MIT, and our money sponsors and our very important cycle sponsors from various programs. So I'll be talking mostly today about molecular dynamics simulations, and I have been doing some of it over all my professional career, but and this was a kind of time when I was mostly working on multi-scale simulation methods, but since about 2015, I'm coming back, and probably from what I will describe, you'll understand why and how that happened. So the context of my work since maybe 25 years ago or so was advanced simulation computing, a program of NNSA which focuses on predicting with confidence the behavior of nuclear weapons through comprehensive science-based simulation. In my neck of the woods, there is material strength and damage. We're trying to predict how strong materials would be, how they respond to straining at the conditions where we cannot test them. So we'd like to accurately predict the behavior there. And so since about 1995, when this program was first established, has been realized that when it comes to predicting strength and plasticity of metals, we can build a sort of from ground up, sort of bottom up modeling hierarchy where we compute parameters, say, with density functional, atomistic simulations, feed them into some mesoscopic method, which I'll talk more about dislocation dynamics here, and then to continuum engineering calculations and so on, and then we can actually predict how a part will behave under appropriate conditions. Okay, so, and the idea of this is because there's a huge gap between scales here and scales there, and it has been realized that perhaps the weakest and most uncertain sort of link in this multi-scale hierarchy is a mesoscale, is between atoms and continuum, and perhaps therefore highest potential payoff. And from day one at Lawrence Livermore, I went and started to work on these things. And I should just say, maybe a little brashly, is that in the past, the connection between dislocations, which is basic ingredient of this simulation method, and engineering models that you want to use here, has been mostly inspirational or motivational, and we sort of embarked on trying to change that. So this is what a dislocation is. It's actually a transmission electron, in situ translation electron sort of movie. What you see is sort of lines sort of looping around, propagating, and so on. These are dislocations. Dislocations actually are made out of crystal disorder in some ways, but you can see them in transmission electron microscopy. And it is the behavior, the motion of this dislocation. As they move, they propagate slip. Crystal planes slip relative to each other. Crystal changes its shape, and then eventually perhaps breaks. And it is the behavior of these dislocations, their motion, that largely defines how much stress or load a material can sustain. So we need to get from here to there somehow. And really first serious step in that direction was taken by Gilles Canova and Ladislas Coben in 1991 when they proposed essentially discrete dislocation dynamics method, where I will say a few things, but this has started to become, rather than just a theory that dislocations are related to that, a computational method to predict from the behavior of multiple dislocations how that happens. All right, so in dislocation dynamics, it is a sort of this mesoscale method in the multi-scale hierarchy. What you do is that you, from dislocation theory or molecular dynamics simulations, you try to understand and quantify how dislocations move under different conditions, how they interact when they collide, and so on and so forth. Then you feed all of this data, all of this understanding in the form of local rules or dislocation behavior into mesoscale discrete dislocation dynamics model. And then you let them just do that and interact and respond to external stress, to their own interaction, and so on. And then you just expect that you get some can predict some almost microscopic behaviors, and some of the most interesting ones have been discussed over the years. I come back to that. Is strain hardening, where when you deform a crystal, it becomes stronger and stronger, or hardens, and sometimes it happens in various stages, not very monotonically like that. So it has been a mystery why. Now dislocations also form. Jafar actually showed you some of the similar pictures on Tuesday. Formed rather intricate patterns depending how you deform the crystal and so on. And to predict how they form, what they are, how they come about was another important goal for the dislocation dynamics method. But interestingly, and many other things, it was a lot of fun to develop this method, but somehow all these coveted connections between individual dislocations and all of this sort of behaviors has always remained some time away into the future, almost like with commercial fusion. Meanwhile, this is what happened was happening in the world of HPC. What you see here is a plot of a theoretical peak performance in flops, logarithmic, obviously, as a function of year. And this is where ASK program started. And this is about where dislocation dynamics model method was proposed. And you see it was going steadily. This is actually an old plot. It goes up to 2019 only. But nevertheless, this is what happened since then. The peak flop rate increased from the time when dislocation dynamics method was proposed, 91 to 2019, about 7 orders of magnitude. While computing capacity increased over the same time interval by 8 orders of magnitude, and perhaps most mind-boggling, what happened to the cost per gigaflop of computation. So in 1963, that was $165 billion per gigaflop. There was no entire capacity of the world was below that. But in 1993, that was about that much. And you see that this is, 6 orders of magnitude. It's quite impressive. But if you count orders, I'll count for you. It's actually 14 orders of magnitude to now. All right? And that is actual real number from Frontier. And over those years, I was like, oh, man, maybe I can do some of the things I do with dislocation dynamics, I can go back and do with molecular dynamics. And that's what we embarked to try to do in about 6 years ago or something like that. First, I need to show you what exactly you will be seeing. I will be showing a bunch of movies, but the movies are essentially all of the subsequent simulations I'm going to show are essentially all of them are large-scale molecular dynamics simulations. And there are so many atoms there that you wouldn't see anything if you just look at atoms. So what we're going to do is we process them and reveal dislocations only, and you will also appreciate how much savings and the degrees of freedom it gives you if you go from all atoms to dislocations only. Okay, so this movie is actually based on a relatively small model, just an illustration. It was made by. Oh, sorry, I need to say, yeah, this is what I was showing. Discussing that why I want to do that. Can we do this now, jumping around the dislocation dynamics, okay? And this is what I want to show you now. This movie doesn't run by itself. I need to start it from the screen. Right, okay, it started actually. Right, so what you see is all atoms, but some of them were determined to be defective in some ways. So we detect them all, they're shown in gray. We delete all others, perfect crystal atoms. What remains are some sort of defects. Then we surround them by some surfaces. This is all method by DXA method developed by Alex Stukovsky. Oops, what did I do? Oh, I need to do it again. Okay, so one. And core performance. Right, so we do this. Most atoms are deleted. You see them here, but from far you don't even see it there. But it's a smaller model. Most of the models we run are much larger. So we select defective atoms, separate them from the rest, delete everything else, and surround them by some meshes. And within this mesh, we can compute what is the biggest vector of this dislocation, which is the amount of slip it carries around as it moves. So this is done on one single snapshot. It's all static for now. And then you can reveal in color or present in any way you like your dislocation lines, and you can do it for multiple snapshots and watch what happens to all of these dislocations and so on. So at least with this sort of renditions, you can see inside and try to begin to understand what's going on there. With all atoms, it's totally impossible, even on this small model, but on large models, it's just hopeless. Okay, so, and that's what we started to do. And a typical simulation setting is what we do. And by the way, please ask me questions anytime. I mean, I realize that I probably go too quick.
What kind of machine are they?
All kinds. It's mostly metals, but it doesn't. This can be done on pretty much anything you have interatomic potential for. But we of course we're interested in crystalline materials, mostly metals. Some of them are listed here actually. So tantalum, tungsten, aluminum, copper, and so on and so forth. This particular simulation I start with is of tantalum. Typically, the simulation are on the scale of from 6 million to 56 billion atoms. This production simulation. Of course, you can run for a few time steps a little larger, but these are production. And this particular one was crystalline BCC lattice of tantalum in 3D periodic boundary conditions. We sourced dislocations, initial dislocation sources. You see them sort of faint hexagonal-shaped loops, these green ones. These are actually dislocation sources. And again, you only see the DXA rendition. All atoms are deleted. This particular simulation was 300 million, modest sized. We're straining along one of the periodic box axis. Okay, let's see. Yes, so that's the box. We'll just zoom out and begin to compress it vertically, and dislocations begin to move around, multiply, form dislocation networks. It's all done in this case at constant temperature. We allow lateral relaxation, Poisson effects, and we can look inside and see how these dislocations organize themselves and so on. And up to that point, simulations of that scale in this context were thought to be unthinkable because you need to not only run large, but also long. Yes? Mm-hmm.
So can you comment on the rate of straining? And
this is high rate of straining, and these are rates of straining we're interested in. So yes, you cannot afford to do it at a quasi-static yet, and probably not forever. Yes. Right. So we then continued, and there was some interesting results we can get out of our very first simulations. It turned out that if you take a crystal populated with dislocations and begin to deform it like that, and subject it to all kinds of complex deformation trajectories, you do it that way, this way. So regardless if you, in the end, hold it long enough under unchanged straining conditions, same temperature, rate, and so on, you actually get to exactly the same steady state flow, crystal flow. So your flow stress becomes the same regardless. There are actual multiple trajectories shown here. Likewise, the same happens to dislocation density, and whatever other measure of microstructure or whatever else you can see become stationary when you reach these conditions. So that was pretty cool. And you can do things like this. You can knead the metal. So you deform it first along one dimension and then along the other one. And what you see is that stress remains over the cycles exactly the same. We can probably continue it indefinitely forever. So to knead the metal. And that was probably the one most interesting physical result out of this. It was hypothesized by a few people, but we kind of show it pretty directly that there is a stationary flow state of these metals, and where it really attains a state of steady asymptotic plasticity, and there must be something like dynamic equation of state that describe these behaviors. But in reality, this first publication was just a, whoa, we can do that. Great. We then continued to think maybe we can do a little bit more than just demonstration and take on this coveted targets in dislocation theory in physical metallurgy. In particular, try to describe, to actually understand why is that stage hardening happens, that you strain the material and it's the stress actually first increases. It's always increases, but increases first slowly, then faster, then slower, and all these stages, that ignited so many arguments over the years. Can we do that? Can we understand directly from MD what's happening? And or can we, observe formation and origins of these intricate dislocation patterns? We have done this. This is still in the analysis stage, but this is the next series of slides. So in trying to see what's the origin of this stage hardening, we related our work to a classical paper by Takeuchi, published in 1975, where what he did is that he took different single crystals oriented in different orientations relative to the straining axis, and orientation is given, marked here, labeled with the Miller index of the axis. Okay, so this 111 and 112, it means is that the different crystals are differently oriented with respect to straining axis. Otherwise, all the straining conditions were exactly the same, and so we went ahead and simulated all exactly the same crystals with MD, and we obtained these results. This is a little bit too small, but if you look at the indices and so on, it is strikingly similar. So how the ordering of this and the relative shapes of these curves are remarkably similar to the Takeuchi results. And this is despite 10 orders of magnitude difference in the straining rate. That relates to your question, okay. So, but if you tell me that this is accidental, I wouldn't believe that, so it couldn't be. And what, in addition to having done this, very great work, the beautiful results, Takeuchi also traced for each one of these crystals, he traced whether the crystal was rotating as you kept straining. Some crystals rotate, some crystals don't. And so we did the same thing. We tried to see if the crystals rotate, and this is what happened. So just to summarize, these are the crystals that Takeuchi tested, and the same crystals we tested in our computational experiments. And disregard this, it's something else. But basically, what happened is that you see stage hardening, this slow, faster, slow, or see parabolic hardening, no such thing, it just basically goes and levels off, depending on whether the crystal rotates or not. If it doesn't rotate, there is no stage hardening, it's all parabolic. If it does rotate, it is stage hardening. We've done a lot more other orientations, always like that. And it's essentially, we can say, with considerable confidence that stage hardening is caused by crystal rotation during straining. Okay. I'll show you a couple of examples. And what you are going to see here is, first example is the no stage hardening. And this crystal is not going to rotate. What you see here is just sort of surfaces, although it's three-dimensional boundary condition, there are no surfaces, of a crystal with 300 million atoms. You see nothing, as I promised, too many atoms to see anything. Here, the dislocations, they're a bit faint, but this initial dislocation configuration, it's a kind of green lines. What you will see here is a stress-strain curve. Stress will be going up and along the strain axis. And here, you will see a orientation of the crystal axis relative to the straining axis in the standard sort of symmetry. This is all of these orientations can be folded in one standard triangle by symmetry. So there will be a dot sort of jumping around here showing what is happening with the axis as we strain. And all of this is synchronized. So this is what happens. Okay, so you see that the strain curve goes like that, and axis actually precesses slightly around this orientation, but it doesn't deviate by more than a fraction of 1 angular degree. And this thing doesn't rotate. And so that's one example. The next one is when actually it does rotate. It's exactly the same meaning here, right? In this case, I don't need to zoom into this corner or any corner. So this is the initial axis orientation. You will clearly see how it rotates. And that is very much coordinated with what the stress strain curve will do. It will do roughly what is shown in this schematic. So initial axis orientation is here, but it will rotate. And as a result of rotation, hardening will be with inflection. Okay. And the crystal rotates. It may not be quite clear from these sort of pictures, but it does. And the rotation was traced by this sort of dot moving, actually overshooting and then coming back to this edge of this triangle. So,
Can I ask a question?
Yes.
How do you actually quantify the rotation? So, I mean, obviously you've got the shearing of the box. So, are you basically, like, how are you actually measuring in the simulation the rotation?
Oh, it's actually, right. So we applied this DXA filtering, so to extract dislocations. And the crystal rotation is actually a side result of that calculation. So it's very easy. Yeah. Right. So that was one of those coveted sort of nostalgic target problems of how do you explain stage hardening in single crystals. And there was a lot of infighting over this stuff over the years. You know, the thousands of papers published, and I think we closed the debate. It's basically all crystal rotation. It's very simple. It's somewhat embarrassing to the past, but it is what it is. We cannot do much about it. We nailed it down, I think. So. As of now, magnetic dynamics at Lawrence Livermore at least, has become the workhorse method for predictive simulations of metal strength. So that's mostly what we do. But we have spent so much time and effort developing dislocation dynamics method. Does it mean that we should just abandon it? Okay. And I need to look at my clock to see how I'm doing. I'm doing all right. And so the question is, should we just really dispense with that? And I'd like to motivate further that it can make sense. This is a workflow in using dislocation dynamics for predicting strength. You begin with some atomistic models with interatomic potentials, and you study how dislocations move. You tabulate these behaviors, and then you feed it again in dislocation dynamics, and then you run large and long dislocation dynamics simulations. These are not cheap. They are expensive too. And you predict strength. Okay, that has been what we have been doing. But now we can just do this. Just have the same interatomic potential, run larger and longer MD simulations, and get the same strength out. Yes?
Can you quantify what you mean by large and long, particularly in the context of, so does DDD let you go to bigger length scales or longer time scales than MD, or are they simple?
DD does. Actually, it's exactly the point I'm getting to, yes. So thank you. Yes. Right. So, and again, there are some benefits of just jumping out around this stage, right? So it is a mature method, MD. We pray to LAMPS. LAMPS is our method, and LAMPS is giving you the infrastructure and essentially like almost a language of atomistic simulations. And it doesn't require much further development. The LAMPS people will take care of that, so it's cool. So, and basically compared to that, it reduces uncertainties to just one single source interatomic potential. Mind you, it's that same source of uncertainties is there, but you add additional ones, most often uncontrolled, whenever you do upscaling in this multi-scale hierarchy. So if you can afford to skip some of these stages, you better do, because you do reduce your uncertainties, right? And it certainly shortens time. If you add together human effort and all of that other stuff, it shortens time to delivery. It probably reduces overall cost of delivering strength predictions to the program. And it, of course, it's unlimitedly scalable to exascale and beyond. But here I'd like to show you that you probably don't want to abandon that. It's too beautiful. Okay. Again, reduction of degrees of freedom going from atoms to dislocations, probably like 5-6 orders of magnitude. So you don't want to let it pass. It's great. But I'm going to run two simulations side by side. And one of them is dislocation dynamics, one of them is molecular dynamics. They're doing exactly the same. They're subjected to the same straining conditions. The dislocation dynamics model parameterized with the exact same interatomic potential as MD simulation, obviously. We place every initial loop source in the same position. It's exactly same loops, exactly the same shape, everything. We could not do any closer to match these two simulations together in terms of describing the same model, right? And even the data we extract it and we keep the data, maintain it, is in exactly the same format. We do it both ways these days, okay? And so this is what happens. You guess which one is which? You cannot tell. I mean, I cannot tell myself. I don't know, don't remember. So they seem to be doing the same, but there's a difference. So this is 200 CPU hours cost to complete this simulation. This is about 1 million. So it's 5,000 difference in the time scale. So then the question can be, why the hell you do that? It's so much more expensive. So, okay, I motivated a little bit, but that's still, you know. But there is another interesting thing. So when we try to, they look to do exactly the same, but they're not really behaving the same way. So what is shown here is that when we analyzed how the flow stress behaves in this simulation and that simulation, they're quite different. I'm not showing that. But even more striking difference was in the accumulation of dislocations. This is what MD simulation predicts. And as I was showing before, all measures saturating if you're just holding your crystal under the same straining conditions for long enough. And that is what's happening. It's basically steady flow. Dislocation density reaches some steady level. None of that happens in DD. Something is going on, something is different. So when we looked what was different, first was striking is that in DDD, unlike in MD, but in DDD, what happens is that there are some very dense tangles of dislocations form and keep piling on top of each other and never really dissolve. Whereas in MD, piles form bundles, but they dissolve. They just come somehow, find ways to resolve themselves, okay? And when we looked still further into what was going on, the difference between these simulations in MD and DD, it turned out that the dislocation nodes are the culprits here. So dislocations, when they collide, they form network, and there are network nodes where 3 or more dislocations sort of join together. It turned out that in MD, these nodes are sticky. They hold themselves and dislocations rather strongly together, and therefore, once formed, they're very hard to resolve and almost never resolve. So more dislocations pile in, the network becomes denser and denser. Whereas in MD, these nodes somehow were very mobile. They can actually resolve all these things, and none of this happens. Yes.
Just out of curiosity, are these two different dislocation networks supposed to be exactly the same or statistically the same?
They are initially exactly the same.
Yeah.
Then they become statistically not the same.
No. I get that, but
Right.
Were they supposed to be statistically the same? Supposed to.
I mean, ideally, you'd like them to be exactly the same, even microscopically, but we didn't expect that. We certainly didn't expect that also, you know. So, right. So, but basically, that's what we found out is what's the difference, what the difference maker between MD and DD. And when this is a simulation that shows that what should be a sticky node in a classical sort of dislocation theory, and this is the node you should be looking at. It should be moving along this blue line, but in fact it finds a way to move in 3 dimensions, okay? And that is the mechanism of removal of these dense tangles. And once we accounted for these mechanisms, this is what happened. A dislocation dynamics model corrected for this mechanism now in action is actually now predicting the steady state flow. Okay. Now, to actually, good thing about this is that again, that's what we're doing. This practice of running the simulations, you know, side by side, and trying to match and observing mismatch between the two is what we call cross-scale matching. And through that, you can improve fidelity of dislocation dynamic simulations that are still 5,000 times less expensive. So, all right. So, X-scale, cross-scale we also use in the context of running just embarrassingly huge simulations, just brute force. They are sufficiently large in our context to be statistically representative of the behaviors where we care for, and yet they're really resolving every tiniest detail of dislocation motion. And there, of course, for these simulations to be successful, you need to have accurate interatomic potentials. You need to run them large and long. But this is what I'd like to spend a few more minutes to talk about. That is a real great challenge. And the rest of what I'm going to show is just motivating us to look at it more carefully. And I hope I can give you a little bit more motivation to look into this problem in your context. And this is rather specific to MD, but I also hope that it's, there are some lessons here to learn for other simulations. So what is MD good for? Is it just an engine to compute a number, which it is? We can compute strength, and that's what we need. Or is it a really fully resolved computational experiment to learn from? I hope it is both, but and it used to be. And this is some sort of nostalgic pictures of Bernie Elder and Tom Wainwright and Shirley Campbell, who was actually the computer programmer. They didn't know how to write code, but she did. They looked at the very first simulations, probably started about 1955. They looked at the melting and two-dimensional system of hard disks, and you see that there are trajectories of each disk, sort of plotted. See how the time progressed. But this is the crystal, and this is a melt. And from the 64 atom simulations in 2D, they could quantify conditions where melting was happening. And subsequently, from a simulation with 108 atoms, it's not 10 to 8, it's 108, okay? They got some great insights into long time tail hydrodynamic interactions, okay? This is amazing, and I I'm old myself to remember seeing these computer movies, like you tape the entire trajectory and you look at these jiggles and wiggles and try to feed your intuition what's going on there. Hey, this is what we have now, and actually this simulation is 6 years old. It was run lumps on Sequoia. In 2017, it was completed. This simulation took about 20 days of full Sequoia equivalent to complete. A lot of cycles used. And that was about 2.1 billion atoms, and it was simulated to 5 microseconds. So it was large and long. And that's why we call it big, LBB. So simulation size in MD simulations usually measured in this measure. It was 10,000 atoms times seconds. This is important data. It's produced about 90 exabytes of recordable trajectory data, which is 6 Googles. Google is estimated total worldwide Google warehouse storage capacity estimated to be 15 exabytes. So what do you do with this data? So what I did with this data is what you usually do with MD data. I recorded as much as I could. Every 100 time steps, I recorded one snapshot, and then another 100 time steps, another. That's what you do. That amounted to about 1 petabyte of data. It has taken 2 months to transfer this using a parallel H-star to storage. Okay, and then I was yelled at and had to reduce it to half. It has taken about 5 months to post-process this data into these dislocation snapshots to reveal dislocations and other defects. And I spent hours watching this humongous movie, and I didn't get very much from it. So what I did observe is this, that between most of the snapshots, subsequent snapshots, nothing happens. Really, the same network there, okay? But then between some, so much happens that you don't see where it happens and what exactly happened, because it's all reorganized, okay? It's avalanche-like, okay? So you know that a lot of the dynamics are intermittent, but because of you saving at the equally spaced time intervals, it's all of this irrevocably lost. So relatively few insights was gained from just watching this thing, or even trying to analyze any of this, because you missed most of the interesting stuff. So now going to El Capitan, which is should come online in the end of this year. The same simulation would take approximately, give or take, 5 hours on full El Capitan. At its maximum efficiency, parallel I/O run concurrently all the time with the simulation itself would only be able to write about that much of the trajectory, so you're irrevocably going to lose much of it anyway, whatever you do, right? So that would feel about 40, this much will still feel about 40% of the disk of El Capitan, which is estimated to be 1 exabyte in capacity. It would take about that many years to transfer to storage, an ungodly number of years to yes.
Isn't that making a case for on-the-fly processing and like
Yes, and that is the case I'm making. Yes, okay. So, yeah, and even this immense effort, if I continue to do as I was doing, would not give you much. So that's what I'm saying, okay. So yeah, what we're facing is that a really growing disparity between the rate we generate trajectory and rate we can actually sort of do anything with this data or even save it. But then the question is like, that's how I think about it, and that's highly speculative. Why do we want to run these large simulations, you know, at exascale and beyond? I mean, the honest answer will be because we can. But also, it only deserves a very large simulation. If you really need to have your system go through need this large volume and long time scales to see your simulated system go through a statistically representative number of essential events that are essential for entire system dynamics, right? And I actually think that there are not that many that you need. It's always a finite number. I don't know what number is, but a finite number. But the rest of the exascale MD trajectory is grossly redundant and repetitive. So we have to do something about it. And we do know in this particular simulation, if we repeat LBB simulation of El Capitan ever, I know for certain that I should be able to record and keep all that data that I need to know about the system's dynamics in below 1 terabyte of space. And this is the total. And this is how much we should be able to reduce, but we don't know how. Okay, so, and this is what the desired specs one would would like to have on the exascale data management pipeline. It has to do some intelligent data reduction. It should filter out redundant, repetitive data, but retain the essential events. This, your question or replica, the data reduction should be performed on the fly, or you will indiscriminately lose the data anyway, right? The computational data reduction always entails computations, but the cost of that computation should not perhaps exceed the simulation itself. Better be a small fraction of it, but you know. And in the end, this reduced data should be possible to post-process to sort of recast it into a shape amenable to human analysis. So that is, yes.
But with MD like scaling really well to large machines and things becoming more and more efficient, isn't there necessarily a crossover point where analysis will become more expensive than actual simulation? And isn't that like inevitable? We want more complex analysis and we have cheaper simulations.
Yeah. So you right. It is possible, yes. I am, at this point, these are my wishful thinking, so that's what I'd like to have. Yes.
So it's obviously not completely identical, but how much can you learn from the high-energy physics community? Because all of their detectors already filter out a huge amount of events. So the stuff that's actually being processed by humans is already pre-filtered at a very, very strong level. And I wonder if there's some kind of...
Yeah, frankly, I'm not familiar very much with what is going on, but it's certainly worth learning from, yes. It's certainly not the only context in where this huge data needs to be processed somehow. I try to disclaim that it is my context, and so, but yeah, it's probably, It shows, okay, it just fell asleep. Right, and that's basically what we're trying to think about and work on. And any ideas, suggestions as how to do that, thank you. So we'll look there for sure. how to accomplish that perhaps is very useful and helpful. So, that brings me to my summary. So yes, direct MD simulations now reaching scales and length and time scales were previously unthinkable. And in our context, what we are interested in, and specifically, they're superseding multi-scale simulations. We can actually afford to do things with just straightforward MD. This cross-scale matching practice that we sort of established and now follow in our simulations is very interesting and very useful. You sort of contrast the mesoscale simulations to molecular dynamics and analyze it, and it can serve to greatly improve fidelity of mesoscopic methods, which are still way more efficient computationally than direct molecular dynamics. And when it comes to more human, interesting time and length scales, MD is going to be out of reach. You cannot simulate these things with a quasi-static straining rate or in multiple micron scales and so on. So you still want to do mesoscale simulations, you still want to do multi-scale simulations, but MD increasingly can be sort of overlapping with this, and that brings with considerable benefits to making these mesoscale models more accurate, enhancing their fidelity. And indeed, knowledge acquisition is becoming increasingly difficult. We're basically hitting a data bottleneck. We're generating and will be generating this data with such immense rates. And what we do, we actually, as of now, indeed, we mostly use this large-scale simulations, push-button computational engine. Tell me the strength. Everything else is lost. And that's embarrassing. We should address that. And I actually have one more slide after that. So that's the same kind of plot I showed you in the beginning. It is extended to about now, partially extended. So these are new machines that came about after that plot was completed. Fugaku, Frontier, El Capitan is going to come online. So Frontier is already operational. And so we went above exaflops. What's interesting also is that what's shown here in red dots is the theoretical speed peak of lowest of the top 500 machines in the world, right? So that's not the slowest computer in the world. It's slowest among the 500 fastest, okay. So you see a difference in between 2 orders of magnitude in theoretical peak performance between the top at this moment and the bottom at the bottom 500 at this moment, right? What's probably even more interesting that there is a relatively consistent time lag. A computer that was tops then will go down to the bottom of the same list in about 6 years. It's actually somewhat increasing now. I see that, but I have not quantified it yet. But that's still sort of the observation, and that between 6 or 7 years from now, what is available to Lawrence Livermore, Los Alamos, ND, and probably a few other centers will be available to many centers. And today, all top 500 computers are over 5 petaflops. This is really serious machines. And that's all. Thank you.